The op-amps we'll talk about a little bit more about it. Just to get started here, we just went ahead trying to do it. So there was a reason for it.
Did you stay last period of time?
Yeah, we were just bullshitting.
This
Shorter than
Did you show you guys that?
Did you guys fire that up?
No. Very interesting.
Yeah, that's cool. All right, so chapter 3, hopefully you read chapter 3 because we're not going to go over the whole chapter here real quick. But chapter 3 is, this is a big one. This is the one that we use for, Ohm's Law is one that we use for troubleshooting a lot. This is how we kind of analyze our circuits and stuff. And so, Ohm's Law states that current is direct, Ohm's Law states that current is directly proportional to voltage and inversely proportional to resistance. So what they're talking about is that if I have my circuit, because these are our three basic fundamentals that we always have to have in a circuit. You know, we're always going to have voltage, we're always going to have resistance, we're always going to have current, and then we're also going to have Watt's law, which is power and stuff. We're going to talk about that as we go through. So basically, we can kind of, when we're looking at certain things, you know, if I'm looking at my current and stuff, when it says that current is directly proportional to my voltage, what it means is that if my voltage is on top of my division there, that these two here are directly proportional, meaning that if my voltage goes up, my current is going to go up. And then just the opposite then with current and resistance, that the difference between my current and my resistance is that they're inversely proportional. So if my resistance goes up, my current's going to go down. Okay? And that's a big part of understanding how Ohm's law works and stuff. Because if we're analyzing a circuit and we have a lot of current, then we might want to check. So let's say, for example, we're troubleshooting a circuit here, and we know that I got higher current than normal, and I know that my voltage is constant, but my current went up. What does that tell me about my resistance of my circuit? Yeah, it went down. Okay, so then we know if how much did it go down? Did my current really shoot up? Maybe I have a short. Did it just go up a little bit? Because if a resistor is going to fail, which way does it normally fail? Let's do it this way. So let's say I'm in new trouble. My current went down. We'll do a natural failure here. So if my current goes down, my voltage is constant. My resistance had to do what? Go up. And which way do the resistors typically fail? I think it was one of our questions, wasn't it? Wasn't it one of our question packets on the failure of a resistor?
You mean like another component goes here?
Yeah, but if the resistor goes bad, maybe it wasn't, maybe it's in,
I think you just went over that in class.
But anyways, if on a resistor, if a resistor is going bad, it typically acts like, it'll start increasing in resistance, and then all of a sudden, it'll actually end up burning up and then open up. So if a resistor starts to fail, it'll start to increase in resistance. So as my resistance starts to increase, as that component starts to fail, my current is going to start to drop. So a lot of times I'm looking for failed components like a resistor or something like that that's starting to open up. And we'll take a look at what happens as a resistor starts to open up and what happens to the power of it as it starts to increase as it opens. So that's basically, our Ohm's law, and that's kind of one of our basic fundamentals of what you're always going to know this. You're always going to retain that and use that out in the industry. So that's a good formula to remember. So, and then if you look on, you might want to just kind of keep to page 103, and I was going to print it out, but I didn't get here in time to print it out. But on page 103, I printed this out for you for a little cheat sheet. But there's the pie chart there for, that's a combination of both Ohm's law and Watt's law. We're going to talk about Watt's law as we go through. But that's a good way we can figure out any one of those four, the voltage, the power, the current, or the resistance, by knowing the other two. So if we know any two, we can always find the third item. The third or the fourth item. Alright, so we're gonna like I said, we're gonna kind of go jumping through here. So on page 79, that we were just kind of talking about talking about the linearity of our current voltage versus our current versus our voltage and stuff like that, with our resistor being remaining the same. So what we have is, again, we like a lot of graphs so we can see what's going on. And what this graph is showing us is that because my current is equal to V over R, if my resistance stays constant, meaning at 10 ohms, and I start having a variable power supply and I start adjusting it from 10 volts to 100 volts, as I start increasing my voltage, my current in my circuit is going to be proportionally go up to the same amount. They're directly proportional. So as I start increasing my voltage, my current in my circuit is going to start to increase. And it's going to be very linear. So if we were to graph out this data, we would get a nice straight line. So they're just showing you that how it's directly proportional, how current and voltage is directly proportional with one another. Okay? And then when we get into our labs again, guess what we get to do in our labs? Some more graph. Okay, so this time I'm going to help you out a little bit, but I'm not going to walk you through it. But I'm going to help you out by the end of the class here. I'm going to kind of help you get started. It's a little confusing about what they're asking for, but we like to do a lot of graphs so we can see what's going on. So if I look at this data, I would never be able to tell that my voltage and my current are directly proportional and that it's a very linear line. But once I graph it out, then I can see that it's very linear. If I move up if I go from 10 to 20 volts, I go from 1 amp to 2 amps. If I go from 20 volts to 40 volts, I jump up twice as much. Go from 2 amps to 4 amps. So very linear between the current and the voltage. All right. Let's see. I think. All right. So what I like to do is that it's a lot easier if we can kind of graphically see it and stuff. So we're going to start looking at our worksheets and we're going to start going through our Ohm's law here right off the bat here. So go to your first worksheet. Unless anyone had any questions before we get started on that. So typically this is how our weeks will come. I'll have you read the chapters, and then we pretty much dig right into the schematics. We go right into the schematics and start analyzing up the circuits and stuff. We'll go over some of the key topics in the chapter, and then just start going ahead and start analyzing our circuits and stuff. So you can see here I have what we call the Ohm's law. This is kind of our pie chart. So basically what this is that if we know two items, we can always find the third. So for example, if I wanted to find my voltage, if I cover up voltage, then I know that my Ohm's law then is just equal to I times R. Okay? If I want to know what my current is, I just cover up my I, then I know it's V divided by R. It gives me my current. If I want to know my resistance, I just go ahead and cover up R, then I know that it's V divided by I. So this is always a good thing to do. When you first get your worksheets, go ahead and write down Ohm's law on there. Put it right in there at the pie chart and write it in there so that you know how to figure out anything. And we can also use it for our troubleshooting. Alright, so then our next step is going to be is that you always want to read my notes. You know, see what some of the notes say. You know, so here it says resistors must be removed from the circuit before measuring. So okay, so if you're going to measure R1 out of this circuit or when you're in lab, make sure you remove the resistor from your power supply. Otherwise, what's going to happen, you're either going to damage your ohm meter or you're going to measure the resistance of that power supply. Now you have to be careful. A lot of times people want to just shut the switch off on the power supply. Well, on a power supply, you know, we got plugged into an outlet, and then it's going to go through a transformer, then it's going to go through a rectifier, then it's going to go through a filter, you know, then it's going to go through a bunch of, you know, regulators and stuff, and then it's going to have some outputs. Well, all these circuits are still hooked up. If I just, because I shut off the power here, if I disconnect this, and I have my ohm meter hooked up going across here, I'm still going to measure the resistance of this circuit that's in the power supply. So not just shutting it off is going to take care of it. You have to physically remove that resistor out of that circuit to measure the resistance of it. Otherwise, you're going to measure the resistance of your power supply. And then if you did happen to have your ohm meter hooked up to it and you did turn your power on, there's a good chance of damaging your ohm meter.
So it already sent out 1.2.
Right, yeah, Nick already measured his ohm meter, and what did you say that one? What was it, how many volts? 1.2 volts or something coming out of the ohm meter?
0.2 volts.
Yeah, because the ohm meter has its own built-in power supply, so it doesn't need another power supply to do any measurements. So be careful of that. Physically remove it out of the circuit and do the measurements. All right. Then it says, note number 2, sketch the electron current path on all schematics. Okay? So which way did I say our current flows? Negative positive. We're electron flow. If you start working with the engineers and stuff, then engineers learn whole flow or conventional flow, and they analyze all their circuits going from positive to negative. It doesn't really matter which way you do it. It's just that all our answers still come out the same as theirs and stuff like that, but they analyze their circuits going this way. But we know that, and even the engineers will agree that we have actually electron flows, that we're freeing up the electrons and the electrons are flowing through the circuit this way. But for some reason they analyze it conventional flow. So we were at one time almost thinking about switching it up and so that we can, you know, so everyone can deal with the engineers, but we're a little stubborn in our ways. We stick with the electron flow. But the process is the same no matter which way you go, and the answers still come out the same way. So we want to sketch the electron current path on all schematics, and we do this from now on. So the next 2 semesters we'll be doing this. So we know that my current is going to go from negative to positive, so my current is going to go through, and it's going to go through my fuse. Anytime I hit a component, I want to put polarity on it. So across my fuse, my first sign as I come through is going to be a negative. Then on the other side of the fuse is going to be a positive. Then my current is going to continue on flowing to the switch. And it's going to be negative, positive across the switch, up through my current meter. We especially like to make sure that we get our current paths going through our current meter because there is no such thing as negative current. It's going to go up through the resistor, and that's going to have polarity. So negative, positive across the resistor, and then back into my power supply. These are just showing you how to hook up your voltmeter. After chapter 3, I get rid of these voltmeters. Okay, but right now I'm just showing you where you hook up your voltmeters, your current meters, and your ohm meters. So that's our current path. So you always want to draw that on all your schematics. And then at the same time, then we did it, we indicated polarities on all components. Note number 4 says all resistors are plus or minus 5% tolerance. That's a typical note that you'll see on any schematic. Instead of them writing down the tolerance on all the resistors, they'll tell you what it is down in the notes. All calculated numbers, 4 digits and rounded correctly, and use the correct metric prefix and units. If you're still struggling with that, remember this is on page 10. So go to page 10 if you need to refer to your metric prefixes. Alright, so we're going to go ahead and we're going to analyze a little circuit here. And we got to figure out, we need to know two things before we can find out the third item. So one thing that we know is that we have, so what I always tell everyone is just start filling in all the information you already know before you even dig out your calculator. Find out all the information that you already have in the circuit. Well, for one thing that we know is that my voltage source is 24 volts. So that's going to be my voltage total over here. So you know that I'm going to have 24 volts total. Then over here, I know that I have a resistor of 120 ohms. So I'm going to want to write in 120 ohms. Now, my software doesn't allow me to put in my omega sign, but when you put it in over on your blank, you got to make sure you put in your symbol. But my software doesn't allow me to do special characters there. And I'll show you some of the software that I use and stuff. This is a real simple, free, basic circuit drawing. It doesn't simulate it or anything like that, but for what I need to do, I don't need to simulate these circuits. I just want to be able to draw them up real quick. So I'll show you some of that software as we get along and stuff, some of the software I use. So we know that we have 24 volts, we have 120 ohms, and do we know what the color code is?
Brown, red, black, gold.
Yeah. So let's see, it should be brown. What did you say? The second one was what?
Brown, red. It's going to be brown.
Yeah, it's going to be brown. And what's the fourth band?
Gold.
Gold. It's going to be plus or minus what tolerance?
5.
5%. Alright. So we know our voltage. We know our resistance. Now before we can figure out, what we have to do is we need to have two items on each section. So if I need to find out my resistance total and my current total, I have to have one other item that's in these blank areas, this little section here. Well, one thing is that my resistance total is going to be the combination of all my resistors added up in this circuit. Well, with these being only a single resistor, my resistance total is just going to be the resistance of R1. So on these worksheets, just know that the resistance total is going to equal to R1. So my RT is just going to be 120 ohms. Now I have two items. Now I can find the third item. So how would I calculate out my current?
Volts divided by resistance.
Yeah, so if I want to find my current, I just go ahead and cover up my current on my pie chart, and I know that I gotta have to do V divided by R. So my IT is just going to be VT divided by RT. So if I take 24 volts and divide it by 120 ohms, what do I get for my current?
You said volts divided by.
Yep. divided by my resistance.
So you're saying 24 divided by 120?
Yep, 24 divided by 120.
That's a 0.2.
Here. What did you get? 0.2. Is that in the proper metric prefix?
No.
No, so that's the wrong answer, right? So it should be 200 milliamps. You gotta make sure you get your 4 digits because that was a calculated number. And so what your answer should have been would be 200 milliamps. Let's see, where's my study guide? You got your little study guide there. Got one more thing that we can add on to our study guide. Quick grab that, I guess, a little bit.
Can you grab extra, please? Is that the definition?
All right. On your study guide there, on the bottom of it, it says good to know. And it says, what remains constant in a series circuit? Okay, this is what we call a series circuit. There's only one current path. There's no other branches or anything like that that we can have our current go off to and stuff. There's only one current path and stuff, so that creates ourselves a series circuit. And one thing that's really nice to know about a series circuit is that my current is always going to remain constant in a series circuit. So if my total current at my voltage supply is 200 milliamps, that means I'm going to get the same amount of current going through R1. So once we figure out the current going through a voltage supply, then we can also go ahead and put it into our, going across our resistor, or going through our resistor, I should say. So current always remains constant in a series circuit. Now once we get two items on our resistor, then we can figure out what our voltage is. And what would be the formula for calculating our voltage?
I times R.
I times R. So if I take my resistance times my current times my resistance, what do I get for our voltage? 24,000 volts.
24 megavolts.
That seems a little high.
24 volts.
Yeah.
Should be 24 volts. The problem is that you're not using your. Make sure you're using your exponent. You gotta make sure that when you put it into the calculator, you're hitting 200 times 10 to the negative what?
Negative 3.
3 times my resistance of 120 ohms. Does everyone know how to use their exponent key? Put it in the power of 10. You better use it because you know if you put down 24,000 volts in my quiz, is it right? You'll be getting a welding slip pretty quick. Yeah. All right, so yeah, make sure you're putting in that using your EE key on your calculator or your exponent key and putting that in there because you will get the wrong answers if you don't use that. Yeah. And don't get in the bad habit of converting it in your head because a lot of times they'll do that, but when we get it down into the micros and the picos, your calculator isn't going to be able to handle that many digits, especially when we get to picos. You're going to make errors. So if you're having a hard time using your EE key, make sure you hit up somebody in class here or talk to me or something like that so that we can get that resolved. All right, so it should be 24 volts. Now, there's a couple of little terms here that we need to kind of get straightened out. Now, like especially when we use like the power, when we're going to do Watt's law, And that's going to have another power formula and stuff. So for example, Watt's law, I'm going to just go ahead and do it so we can see where it's used. Watt's law is going to be P for power is equal to IE. Okay? Well, E and B are basically one and the same. Okay? They're both talking about voltage. Both their units are voltage. When we're talking about V, we're talking about a voltage drop across a resistor. When we're using E, we're talking about our voltage source. This stands for our electromotive force, EMF. Okay, so that's our EMF, our electromotive force. That's what's giving our push into our circuit. That's giving us our energy into our circuit to get the electrons to flow. So sometimes V and E get kind of, the waters get a little muddy there. But it doesn't really matter. We both know that the units are voltage, but if somebody's talking about the electromotive force, it's the E. Okay? But the answers are still going to be in voltage, so it really doesn't matter. But you should be understand that there's a difference between voltage and electromotive force. One's our source, one's our voltage drop. Okay? Our voltage drop is created by our resistance. It gives us our potential difference between the 2 points. It starts. What's the definition of resistance?
Opposition current.
Opposition to current. That creates our potential difference across those 2 points. So now, who can we call? Sometimes you'll see it. So sometimes you'll see V, you'll see E, and a lot of times you'll see IR. So basically we can have, so if we're talking about the resistor, we're talking about a voltage drop. Well, that voltage drop and the IR drop is one and the same. Sometimes they call them the IR drops. Because to calculate out voltage, voltage is equal to IR. So a lot of times you'll hear this called, what's the IR drop? What's the voltage drop? But if they're talking about E, typically it's their electromotive force, it's their source. Okay? So there's voltage drops and IR drops. The IR drops and the voltage drops are created by the resistance to the opposition to current in our circuit. Alright. So now all we have to do is just figure out what our current meter is doing here. So A1. So what would be my current going through A1? 200 milliamps. And why is it 200 milliamps?
So it remains constant in the series circuit.
Good. Yep. Because my current remains constant in my series circuit, I'm going to have 200 milliamps of current going through my current meter. So basically what we're going to do is so if we analyzed it, my current is going to come out of my source. I have this potential energy that's coming across, that's being generated by my battery or my power supply. It's going to start creating start going to put pressure onto our circuit. The electrons are going to start to flow. My circuit's going to start to do, as long as I have a good fuse, it's going to go through my fuse. As long as my switch is closed, my current is going to go through my switch. So all my current has gone through my switch. All my current has to go through my ammeter. And when we're using an ammeter, what must we do to our circuit? If I'm going to install an ammeter into my circuit, what must I do? What's that? Yeah, break the circuit. Okay, so yeah, break the circuit. Yeah, there we go. Yeah, so you must break your circuit, and then wherever you break your circuit, you install your current meter. So all my current is going to go through my meter. So when you're talking about the current, it's going through the meter, and it's going up, and it's going through the resistor with the opposition of current going through there. And then all my current is going to come out of my resistor, back in, and then down into my power supply. Okay? So real basic circuit. Now we just only have one more thing, okay, so we're gonna just assume that we removed it out of the circuit, we're gonna measure it. And let's say I measured, say I measured 118.5 ohms, okay? So that's what the value of that resistor is, okay? The color code says that it's supposed to be 120 ohms. We use that for our approximations. We always use the color code for our approximations. We want to measure it to make sure that it's in tolerance, so we measured it, and it actually turned out to be 118.5 ohms. So I go ahead and I throw that 118.5 ohms into my circuit. Here's my approximations. What actually happened to my current then when I threw that 118.5 ohms in there? What actually happened to my total current? Yeah, why not? Because I know that IT is equal to PT over RT. And we said that IT and RT are what? Directly proportional, inversely proportional. Inversely proportional. So that means that my resistance goes down, my current's going to do what? Go up. So for during approximations, everything looks like this, but then when I actually throw the actual value of my resistor into that circuit, then I realize that I got a little bit more current than what my approximations are. So is that an acceptable resistor? Can I throw 118.5 ohms into that circuit? Would that be an acceptable value? So what is that? What is the percentage of tolerance on that? What is the percent difference on that? What's your percentage of tolerance on that resistor? How do you calculate out your percentage of tolerance on a resistor? What's the formula?
Measured current minus the color code current divided by color code times 100.
And so what do we get for a percentage of difference?
1.25.
Is that all it is? 1.25%? So then that'd be more than acceptable, then that we can go ahead and throw that into our circuit there. Okay? So we have to be careful because we have to meet this guidelines. We have to make sure that all resistors are within plus or minus 5% of our tolerance. So when you're typing in your resistors, make sure you double check it on your circuit there. All right. Any questions on that? Pretty straightforward? Okay, good. All right, so then what we do is we do a lot of troubleshooting. Now remember, a lot of our troubleshooting is done with a voltmeter. So on our study guide there, under our troubleshooting, we need to know a couple things about when we're troubleshooting. Measuring voltage across an open. Okay? When you're measuring voltage across an open, you're going to see your source voltage. Okay? So under your troubleshooting guide, where it says measuring voltage across an open, right in there, you'll see your source voltage. When you're measuring voltage across the short, you will read approximately 0 volts. Okay? So when it's an open, it's going to be measuring your source voltage, and when it's a short, you're going to be measuring 0 volts. So we're going to say that for some reason our circuit's not working. Where would be a good place for me to start? What would I want to do? What would I want to make sure that I definitely have? That I want to make sure that
Power sources on?
yeah, make sure your power source is on. First thing I want to do is just double check and make sure my power source is on. So what I'm going to do is I'm just going to put my voltmeter across there. And we're going to say that, yep, we got that. Yep, we're good there. I have all my I have my voltage source.
Work your way up to
Okay? Yep, so, okay, yep, so we got our power supply turned on. Got the 24 volts going across it, but I still don't have anything going across my load there. So what would be my next thing I'd want to check out? Yeah, fuse would be a good thing. So what I'm going to do is, because we don't want to, we could either do one or two things. We can either check it with a voltage meter or we can check it with a current meter. Well, a lot of times we can't shut the machines down. If we're working on an automation line or something like that, they don't want us to stop production. They'll find people to fill in that one section of that station that's down, and they'll just have people take them off the line and stuff until we get it up and running. So they're not going to let us shut it down. So we always have to use our voltmeter a lot of times. So what we're going to do is we're going to put our voltmeter across our fuse. And I measure 0 volts. Is that fuse good or bad?
Bad.
Well,
I don't think so either.
okay, so a fuse, so let's kind of take a look at it. Let's go back and let's just say, let's look at it the other way then. Let's say I ended up measuring, let's say I ended up measuring 24 volts across that fuse. Is that fuse good or bad?
I have that.
Okay, so let's take a look at it. So I got to give you a little hint here. So measuring voltage across and open, if I measure voltage across and open, so I'm measuring voltage, right? So I have, is that fuse an open or a short? It's an open. That means if that fuse is an open, that fuse is no longer in there, right? If it's an open, I have no current flowing through there. So if all of a sudden I measure 24 volts going across the fuse, that means my fuse is open, and I have no more current going through there. Because that open, this is a good thing to write down, make sure, is equal to infinity ohms. As much resistance as I can have in there. I can't have any more resistance than an open. So I have a very large amount of resistance. A short is equal to approximately 0 ohms. Okay? Well, if I have an open and I have an infinite amount of resistance across my fuse, do I have a very large amount of opposition to current or very little opposition to current if I have an open? Do I have a tremendous amount of resistance going across that fuse? Do I have a large amount or a little amount of opposition to current? Yeah, yep, I got infinite resistance going across my resistor.
No current.
No current. I have a very large amount of opposition to current. So my current is not going to want to flow through that fuse. Alright, so we're going to go back to, we did say that, let's just say the original thing there, we said that I'm going to be measuring 0 volts. So I ended up measuring 0 volts across there. So now I know that my fuse is what? Good or bad? Good. It's just like a short, right? It has 0 resistance. It means that it's just like a piece of wire in there. We don't even see that fuse in our circuit. It's just there to protect our circuit. So I have 0 volts going across my fuse. I identified that that's good. Then what would be my next step? What would I want to check next then?
Switch.
The switch. So now I check my switch. So now I go and measure across my switch. And I hook up my voltmeter up to it. And I end up measuring 24 volts. Is my switch open or closed? Open. So if my switch is open, I have how much resistance going across my resistor, or across my switch? How much resistance do I have across my switch? Infinite. Large amounts of opposition to current then. Can my current flow through that switch then? No. It's not going to flow anymore. My current's going to stop. And am I going to get any voltage across my resistor? No. Nope. Because this is going to go down to 0 volts. Because my switch took all the voltage. there's no more voltage left to give to the resistor. So then my voltage across my resistor went down. My current did what? Went down. Yep, went down because I don't have any current flow, so my current went down. What happened to my resistance then? It remained the same. That didn't change. Yeah. And I could go ahead and I could pull it out of the circuit just to make sure that that was still good. But I was pretty sure I just forgot to turn the switch on. Okay. So those are just some of our troubleshooting skills that we go through. That's what the first step is. Make sure we have a voltage source. Make sure the fuse is good. Make sure the switch is closed. You know, my switch might show that it's closed, but I could have bad contacts in there. You know, even though I have it on, I still might not get current until I put my voltage in there and I go, oh, wait a minute. Those contacts are bad. I got bad contacts. Okay? So even though we can't assume that just because the switch is turned on, that it's actually making contact. Alright. Alright, that's good for this circuit. So let's go to... Alright, any questions on this one before I erase it off? Alright, let's look at circuit number 2 then. Alright, so 3-2 there. Okay, what's our first step that we want to do when we analyze the circuit? Yeah, always want to draw your current path and your polarity. So is my current flowing clockwise or counterclockwise? Counterclockwise. It's going from negative to positive, so my current's going through. It's going through my fuse, through my switch, negative positive, through my current meter, negative positive, through my resistor, negative positive, back through here, and then back into my source. So there's my current path. Alright, what's my next step?
Figure out what you know.
Yeah, figure out what we already know. So what do we know about the circuit? Without even digging out our calculator, what are some things that we know about this? We know the current. Then where can I put my current? So we put it that's going across R1. Where else can we put my current? My IT. And why is that? Yeah, current always remains constant in a series circuit. And these are going to be just some of those ones that are going to be repeating all the time. And it's really a big deal when we start working at complex circuits and stuff like that. All right, good. So we got our 30 milliamps in there. What else do we know about the circuit?
Color codes.
Yeah, so we can figure out the resistor value. So what's my resistor value going to be?
1.8K.
What is it?
1.8K.
1.8K. Oh, make sure you give me your units, otherwise I'm going to assume apples or bananas or something like that. All right, so it's going to be 1.8 kiloohms. All right. Do we know anything else about this circuit? Yeah, now we can dig out our calculator. Now when we dig out our calculator and we start calculating our voltage, how many digits does our voltage have to be? 4. And it has to be rounded correctly. So if you see the rounding error up there, make sure you stop and correct your one so we get practicing our rounding. Alright, so what do I get from my voltage saying going across R1? 54 volts. Anyone agree with Josh there? Yeah? Nobody everyone agrees with? 54 volts. How do we calculate our voltage?
4.
I times R.
I get 54 kiloohms.
Okay, watch your metric prefixes. Remember, it's going to be, so there's a, if you do want, well, I don't like to show you shortcuts, but I'll do it this time.
Yeah, I did it
Times
backwards.
30 milliamps.
I did it backwards.
I'll show you the little shortcut though if you don't want to use your metric prefixes. So when you're multiplying powers of 10, what do you do with the exponents? Yeah, add them together, right? So if I add a plus 3 and a negative 3, what do I get? 0. Those two just cancel each other out. So then all I have to do is take 30 times 1.8. Yeah. But I don't like to do that because I want you guys to get in the habit of using your exponent key on your calculator. But that's why we did it a long way when we first started out in class. So remember. So if I take 1.8 times 30, I get what? 54 volts. Alright, so yeah, so even though I don't want you to do it this way, it's a good way for double checking your answer. You know that these two are going to cancel each other out, so you knew that there was probably not going to be any metric prefix at that point. That's a good way of just verifying your answer. Alright, so then what we're going to learn about in chapter 4 is that all my voltage drops added together, the algebraic sum of all my voltage drops equals my source voltage. But since we only have one resistor in there, then we know that my voltage total across from my power supply is going to be my 54 volts. All right, so what can I do next then? Yeah, so I can figure out RT. RT is just going to equal to dt over IT. And I get what? 1.8 kilo ohms. You said that the total sum of all my resistors in a series circuit is going to equal my total resistance. And since I only have one resistor in there, that's going to be my total resistance. Yep. So if I'm looking at it, if I'm the power supply and I'm looking out at that circuit, I'm seeing this much opposition to current. I'm seeing that 1.8 kilo ohms out on my load. Here's another good little thing here. So we're going to start talking about these right off the bat. Because this gets really confusing even for our second semester guys. Okay, here's my resistor. This is my voltage drop. This is my IR drop. This is what we call our load. Okay. The load is just like if you're a truck driver. You know, if I got a pallet full of generators, somebody loads that up onto my semi-trailer, that's part of my load. Okay, I'm loading down my circuit. So when I'm looking at this circuit, so this power supply sees R1 as a load. How much of a load does it have on it? So we call it a load. So R1, and when we're working with these circuits in here, I just drew a blank on what I was going to say. Dang it, I just drew a blank there. But anyways, I know what I was going to say. So when we're working on these circuits here, and I have a load, so we'll call this a load. This load, we represented it as being as a single resistor. But the complexity of this circuit that this load is might be, it could be a light bulb, that could be considered our load. And that light bulb is going to have some type of resistance on it. And that's what we call our load. And every time I add another light bulb to my circuit, this is actually a parallel circuit, but every time I add another light bulb to my circuit, I'm increasing my load. I just put another pallet of generators on my semi-trailer. I keep on increasing the load. And so that's what we're talking about when we talk about loads. That's what we're talking about. How much energy are we using? How much How much work is that circuit doing? How much work is that power supply trying to get to make sure that we can move that load or light up our loads and stuff? So when we talk about one resistor, the complexity of that one resistor could be anything. It could be a network of thousands of circuits. But we use it just to simulate it as one resistor because just to get through our basic fundamentals, we need to understand how does that even work. And so we call that our load. All right. So now so we got everything all completed. We have our current paths, we have our polarities. Everything's all calculated out. And so we'll remove it and put in, we put in 1.93 kilo ohm resistor. I'm sure that's probably within tolerance. We're not going to go through that again. So if I do that, what's going to happen to my current? My actual current then, once I put in that resistor in there. It's going to go down, right? Because I is equal to C over R. And if R went up, right, compared to what we approximated, it means my current had to go down. What's that? Is it? How do you figure it out? There's no, maybe it might be. That would be what, about 130 ohms extra? Huh? 5% would be 90. Yeah, so it would be out of tolerance. I like that. Good approximations there. Yeah, so that would be out of tolerance. So we couldn't throw that one in there. So now when we talk about, now here's our approximation. Our R1 was 1.8 kilo ohms. We actually put in 1.93 kilo ohms. Our current across our load went down, right? So now referring our resistance as a load, and this is where people really get confused. Did my load increase or decrease? Well, just take a guess. What would you think that load would be considered as? An increase or a decrease?
Increase.
Yeah, it's actually a decrease. Okay? So it's kind of opposite of the resistance. Okay? Because if I put in a 1.98 or 1.93 kilo ohms in there, my current went down, right? So if my current's going down, it's not working as hard anymore. And we'll see it when we get into power and stuff. We'll take another look at it. But I wanted to introduce it right away. So on this one here, my load is actually went down. I'm not working in its hard. I'm not drawing as much current. Power supply doesn't have to work as hard because it doesn't have to supply as much current. Still going to supply the same amount of voltage, but it didn't have to supply as much current. So it didn't have to work as hard. So our load actually goes down. If our resistance goes up, our load goes down. So that's something good to think. If R goes, how do I want to say it? That R is directly proportional to, or inversely proportional to our load. So if R goes down, my load's going to go up. If my resistance goes up, my load's going to go down. And we're going to really be looking at that when we get into parallel circuits. That's where it really plays a big factor in there when we're talking about loads. Like if I plug something into these outlets, the more times I plug something into any one of these outlets, I'm putting another load on my circuit. I'm getting charged more. I'm going to be getting charged for the kilowatts. And you should have read that in chapter 3. They talked about the kilowatt hours and stuff like that. So the more stuff I have plugged into my outlets, the more kilowatts per hour I'm going to be getting charged. All right. Let's see. Alright, if I measure my fuse and I measure 24 volts or 54 volts, is my fuse good or bad?
Good.
Okay, how many people say good? Raise your hand. How many say bad? Yeah, it should be bad. Because when we measure across an open, we measure what?
Your full potential voltage.
Yes, my source voltage. So if that fuse is open, if that's open, it has how much resistance going across it? No, not zero. Infinite. Don't get another thing that people always get confused by is that infinite and zero.
Resistance is opposition.
Yep. Yep, there's the opposition to current, so if I have a lot of voltage, I'm getting a lot of potential difference across it. It means I have a lot of opposition to current, meaning I have very large amount of resistance. So yeah, it's infinite resistance, not zero, it's infinite.
Zero current.
If I was measuring 0 volts, so if I'm measuring 0 volts across it, now it's a short, and it would be like a piece of wire which has hardly any resistance at all. Alright. Alright, let's take a quick 10-minute break here, and went by fast here. And then we'll jump on to a couple of other worksheets here. One's with power here, so we can get those covered.